Okay, so this video is just going to go through the topic of work, energy, power. So it's topic 10. This topic is important because work, energy, power tends to come up as part of another question and not so much as a standalone question. All right, so it's quite important now for everything that we're going to be doing, moving on to, especially circular motion and simple harmonic motion. But more importantly, when we hit electricity next year, that's going to be vital, because with electricity you have to learn that power equals power, if you will, energy equals energy equals energy. As these kind of concepts, we'll go through them now. So the first thing we're going to look at here is the idea of work. What is work? Work is the force required to move a body through a displacement. Note that word, not distance, displacement. And the equation is W equals Fs, or work equals force times displacement. Okay, so in other words, the higher the displacement you have to go, the greater the amount of work you'll have to do. For example, the reason it's displacement, not distance, is that if you have, say, stairs, like, okay, all right, well, your distance on the stairs is, we shall say, 2 meters. But your displacement, which is from your start position to your end position, is only 1 meter. Okay, so your displacement then is not the distance you traveled, it's your displacement from when you started to where you finished. Okay, so that's the idea. So on a stairs, you'd be 2 meters running up the stairs, but you're only 1 meter off the ground. So your work done is only the force you applied times the 1 meter off the ground. Okay, the SI unit is the joule. Okay, and you could also refer to as 1 Newton meter. So if you forget that it is joules, just look here. Force is newtons and displacement is meters. Okay, so Newton meter will also be accepted. But please try and remember joules. The reason joules is important is because all joules equal each other. Okay, so work done equals potential energy equals kinetic energy. Okay, so energy all the same, and work done is one of them. And everyone forgets about work done because it's not called an energy, it's called work done, and everyone forgets about it. So try and remember that. Okay, in the log tables, they're all in the one page. So if they're all on the one page, that's not true. But they're all on the one page. So you can try and remember that most of them, because I think power is there as well. Most of them share the same SI unit. Okay, joules, which means they're all the same thing. Okay. So the first question here, find the work done when a 10 Newton force undergoes a displacement of 30 meters. That's fairly straightforward, guys. So W equals F times S. Okay, and your answer should be 300 joules here. Okay, number 2, what is the weight of a mass of 100 kgs? And then find the work done raising the mass. So again, write all your things on the left hand side. I kind of skipped this step in the first one because it was just very short. So 100 kgs. Vertical height, that's our displacement. And we're looking for work done, force times displacement. So what is the weight of a mass of 100 kgs? Okay, so I'll give you a second to think about that. What's that? For weight looks similar, but it's different, is mass times acceleration due to gravity. So that's going to be 100 times 9.8, which should give us 980 newtons. You see, weight is in newtons. All right, and then find the work done. Yeah, okay, so the work done, force times this. Oh, and actually, anyway, if you didn't know how to answer this, okay, you would have to figure it out here, because we needed a force, not a mass. Okay, so force is mass times acceleration. So of course, F equals mg is 980 times 60, which gives us 58800 joules. All right. Problem 3. A man of mass 105 kgs climbs up a ladder of length 10 meters, which is inclined at an angle of 40 degrees to the horizontal. Find the work. Okay, so generally a lot of these questions, I do it because I find it hard to try and keep track of everything in my head. I need to write everything down. I do advise you do the same. It makes it a lot easier to answer these questions. You're not going to get extra marks for answering it all in your head. Okay, so put down as much information as you can. So mass of 105 kgs. ladder, so displacement, no it's not, sorry, length is 10 meters. Okay, so we have a ladder. I'm going to draw it over here. And the ladder is like this at a 40-degree angle. So my pen for this tablet isn't the best. Okay, and this distance is 10 meters. Okay, find the work done by the man going from the bottom to the top of the ladder at a constant speed. So he's going from the bottom to the top of the ladder. So we're looking for the work done equals force times displacement. Okay, so work done equals force times displacement. The mistake a lot of people make now is they get the force. So force is going to be the guy's weight. So it's going to be 105 times 9.8. So the force should work out to be, what did I get for that? 1029 newtons. Okay, 1029 newtons. Now, they say 1029 times 10 is 10,290. Question solved. You're wrong. Okay? The reason you're wrong is that 10 meters is the length of the ladder. It's not your displacement. Remember what I said? Your displacement is from where you started, which is on the ground here, to where you finished, which is above here. This is your displacement. So we need to find that S value. Now, if you look at this, what do we actually have? We have here a right angle triangle, hypotenuse of 10 and an angle of 40, and we're looking for the opposite. So we simply use trigonometry. Okay, so we use trigonometry. That didn't really come up very well. Alright, so we use trigonometry on this. Okay, so to find S, we say S is going to equal, actually no, I'll if we're going to do trigonometry, okay, we go with sine. Okay, so sine, our angle, equals the opposite over the hypotenuse. Okay, and we're obviously looking for the opposite, so the opposite is equal to the hypotenuse times sine of the angle. So that's going to be our displacement times 10 sine 40. So when you put 1029 and 10 sine 40 into this equation up here, we should get our work done to be 6614.28 joules. Okay, so the trick to that one is people would put 10 down as the displacement. 10 is the length. That's the length you climb up the ladder, but it's not your displacement. Okay, and double check. Okay, there's a second part there. How much work would the man do if the ladder was vertical? Okay, well that's fairly straightforward. In other words, that I'm going to rub out this diagram. Oops. I'm going to rub out this diagram here. So basically now what he's done is he's put the ladder vertically up along the wall. So that's very straightforward. It's just going to be your force that we had here, 1029 times 10, because 10 is now our displacement. That's it. Okay, and your answer there for part 2, I'll put down the answer there. If you have any difficulties, leave it in the comments and I'll get back to you. So your answer for part 2 should work out to be 10,290 joules. I can't squeeze it in, but joules. Always give your SI unit. Remember, guys, you will not get marks for giving the SI unit. However, for every time you forget to give an SI unit in your final answer, they will take a mark off you. Okay. All right. So energy. You've seen this before in junior cert. You've seen it now again. But basically, what is energy? Energy is the ability to do work. Okay. Energy is the ability to do work. Okay. My highlighter doesn't seem to want to highlight. Fair enough. My tablet will do its own thing. Anyway. So energy is the ability to do work. Okay. So the idea of this is that without energy, you can't actually do anything. Without energy, you would, of course, die. Okay, the reason you would die is because you wouldn't be able to, your heart wouldn't be able to beat, your brain wouldn't be able to process, your lungs wouldn't be able to move. Okay, but then in everyday life, the ability to move, the ability to do anything requires energy, and that's for everything, okay? So energy is the ability to do work, okay? All right? And of course, energy, SI unit, joules. So energy and work done are the same thing. So if you run up the stairs, you did work to get up the stairs, but you also burnt energy, okay? Now, there's a list of energies here, okay? We've kinetic, potential, electromagnetic, internal, chemical, and nuclear. For physics, for the physics course, the ones you need to know and the ones we will cover are kinetic, potential, electromagnetic, which we'll get to when we get to electricity and radiation, and nuclear energy, okay? Internal energy, if heat is applied to a substance, the motion of its molecules increase. So that ties in with temperature slightly, but we don't really talk too much about internal energy. We talk more about conduction, convection. Chemical energy, the energy given out in the form of heat, light, or kinetic energy during a chemical reaction, we don't really touch on. If you do chemistry though, you'll see that, okay? The thing about these is they're all the same. They all equal each other. Sorry, they're not all the same, but they all equal each other is what I mean, okay? Equals that, equals that, equals that, equals that, okay? Because the kinetic energy you have corresponds to your potential energy. So for example, if you have a ball and you have the ball in your hand and the ball has no kinetic energy, it has a lot of potential energy. When you drop the ball, the potential energy as it gets closer to the ground goes down and the kinetic energy goes up, okay? So what you lose in one, you gain in the other, okay? Electromagnetic energy we'll come back to that when we do electricity. And nuclear energy we'll come back to next year when we do modern physics and nuclear physics, okay? All right, so for today, we're just going to focus on these two, okay? And as I said earlier, just 2 seconds ago there, conservation of energy, okay, states that energy cannot be created or destroyed. It can only be converted from one form to the other, okay? So there's no magic solution to energy, okay? You can't just snap your fingers and create electricity, okay? It has to come from somewhere. You have to convert one substance to something else, okay? So you have to convert. Generally what we do is we convert potential energy into heat energy, so chemical energy into heat energy. So most electrical power plants that work in Ireland, sadly, because we're behind the times here when it comes to renewables, is we burn coal and gas. I think gas is the big one for Ireland, okay? So we burn gas. So what we're doing is we're taking the chemical potential energy of the gas, we're igniting it, burning it, turning it into heat energy, which boils water, which turns a turbine, and away you go, okay? Now, for us, this is key. What you lose in potential, you gain in kinetic. And what you lose in kinetic, you gain in potential, okay? So in other words, the total energy, okay, that you have is your potential energy plus your kinetic energy equals total energy, okay? One will always go up, the other will always go down. Potential and kinetic won't both go up, okay? If one goes up, the other goes down. If one goes down, the other goes up. That's kind of generally how it works, okay? The kinetic energy, what just happened there? All right, the kinetic energy that we have is EK equals a half mv squared. All right, what is kinetic energy? The energy an object has due to its motion. If you're asked for this definition, you have to give this, you cannot give this, okay? You have to give that energy has due to its motion, all right? EK just basically means, I always call it an EK, in the log table it's down as EK. In the exams, you could just say E, but I always recommend give EK just for yourself. It's a lot, because sometimes you could have potential kinetic and other types of energy flowing around there. M is the mass of the object, and V is the speed of the object, okay? So obviously, the faster you're going, the more kinetic energy you have, okay? Mass, the larger your mass, the more kinetic energy you require, okay? So for example, so you have two cars, and that's why sports cars, actually racing cars, Formula 1 cars, are very, very light, okay? They try and make them as light as possible, because the lower the mass that they have, okay, the less kinetic energy they require to move, which means most of it goes into speed, okay? Whereas if you've got a really, really heavy car, look at a tank, okay? Tanks are incredibly heavy things, okay? Their mass is super high, so their speed is generally not that fast. And their kinetic energy is also high because they need to drive that heavy mass and move it, okay? So that's the way to think of it, Okay, so kinetic energy, it's related to how fast something goes, is related to the amount of kinetic energy something requires, relies on the size of it, the mass of it, and the speed, okay? And vice versa. Okay, that keeps happening, I don't know what's going on here. And vice versa, the speed of an object relies on the kinetic energy it can pump out, and of course the mass of the object, okay? So anytime work is done, energy is transferred. Okay, so every time work is done, when you run up the stairs, energy is transferred. Okay, you transfer your energy into motion. Okay, kinetic energy to run up the stairs. Okay, and we get our energy from, of course, our food and our diet. All right, so it loses energy. So this means when a body does work, it loses energy. Energy is transformed. Okay, the example is simply electricity. We convert that to light and to heat in a light bulb, okay? And it loses energy. Heat goes out, okay? We lose the heat and then the heat gets converted, okay? All right, so a body of mass, 20 kgs, has a velocity of 12 meters per second. Find its kinetic energy, okay? So list everything on the left-hand side. Mass is 20 kgs. Velocity 12 meters per second. EK equals a half mv squared. As you probably noticed by now, my tablet does not pick up my pen at all. Well, it does sometimes when it wants to. So you basically just put in your values and you should get your kinetic energy to be, what did I get there? I did this earlier, so I got 1,440 joules. Okay, so 1,440 joules is your kinetic energy here for this one. Fairly straightforward one. Okay, so the next one though is typical of an exam paper. So what I'm going to have to do is I'm going to read the question and I'm going to have to roll it up to the blank. Just because I need the space here. So a bullet of mass 4 grams with a velocity of 200 meters per second penetrates 0.5 meters into a block of wood. Find the force that the wood exerts on the bullet. Part 2. Calculate the velocity with which the bullet emerges if the block is only 0.25 meters thick, assuming the same opposing force. Okay, so we're basically shooting a bullet into a block, and the block of wood, we don't know how thick it is, but the bullet only gets 0.5 meters into it, and it's done. Okay, the second part is if we shrank the block of wood. Okay, so we had a block of wood that's only 0.25 meters thick, but it could still put in the amount of force to slow down, okay, the wood. Because if you remember back, Newton's laws, every action equal but opposite reaction. So what the block of wood is going to do is it's going to try and slow down that bullet to the same rate as before. But obviously it's not going to do it because it can go 0.5 meters into the block. Right, so we'll start with the first bit. Okay, I don't know why that keeps happening, but it's incredibly not helpful. Anyway, so I'm going to write out all the information. First, we're going to start with part 1. So the mass equals 4 grams. So that's 4. Actually, instead of doing 4 by 10 to the minus 3, I'll decimal point it. It'll be easier for me. 0.004 kgs. Velocity, we don't know. It penetrates 0.5 meters into a block of wood, so that's my displacement is 0.5 meters. Oh no, the velocity we do know, sorry. The velocity was 200 meters, apologies. I thought I was looking at part 2 there, meters per second. Find the force so we're trying to find force, so we need to find F equals F. Okay, so if we fire a bullet into a block of wood, okay, and we're trying to find what's the force of the bullet, so every action has an equal but opposite reaction, okay, so therefore, right, so what we have to find out what equation can we use for this, okay, so we have F equals ma. Now obviously that's not it, okay, because we do not have enough information to find the acceleration. Okay, we don't. We have the mass of the bullet, 0.004, but we do not have the acceleration. So we can't use F equals ma. So what other equation can we use here? Okay, we could use work done equals force times displacement, or F equals work done over S, because we have displacement 0.5 meters. All right, so we're almost there. So this is what we're going to have to use. We have to find this. We have to find the work done. Okay? What else does work done equal? Can you think? Work done equals potential energy equals kinetic energy. So what we need to find here, so work done equals EK equals EP. They're all the same. Okay, they all mean the same thing. Well, they all mean different things, sorry, but they all have the same values. Okay, because obviously the kinetic energy can only be the same amount as the potential energy, and work done can only be the same amount as them. Okay, so we're going to obviously do kinetic energy because we haven't got the potential energy yet, and we also don't have enough information for potential energy. So we're going to look for EK. Okay, so EK equals a half mv squared. A half mv squared. Do we have enough information? We have the mass, we have the velocity. Yeah. Put in your mass of 0.004, your velocity of 200 meters per second, and we should, and don't forget, what a lot of people forget to do, squared V. Okay? And when you put that into your calculator, please do the following. Go bracket 200 squared, close bracket. Okay? Sometimes calculators, if you put the square outside, no brackets, for some reason, I don't know why some calculators will do it. They shouldn't. They should work in the BIMDAS method, but sometimes they just don't. I don't know why. But I have seen calculators, if you put the square, so you have, say, 0.004 times 200 squared. Sometimes I have seen it happen where they'll multiply the 200 by the 0.004 and then square that answer. So just to be safe, put it in the brackets. It's easier. Anyway, that gives you, or should give you, 80 joules. Okay, so we have 80 joules there. Okay, and then all you do is you sub this back in up to the top equation here. That's all you do. So our force should now be 80 divided by 0.5, and it should give you a value of 160 newtons. There you go. That's it. All right, fairly straightforward. Okay, the difficulty with these kind of questions is where do I start it? Once you start, but always try and remember. Okay, go to the log tables, find a value with one missing value. Okay, now in this case, no such equation existed. Okay, no such equation existed. So instead, we had to find. Okay, well, what are they trying to ask us to find? What information do we have? Okay. All right, so no equation existed with F and one missing value. But what you did know, what we should have noticed, is that what did exist was half mv squared. Okay, we're doing a mechanics question, so obviously you stay to the mechanics section and you find EK equals a half mv squared. We have all that except the EK, and then you should try and put it together and realize then that, well, hang on, if I get E and E is the same as W, then that means you can find that equation. Okay, so you have to piece it together. Okay. If the value you're looking for doesn't exist in an equation with one missing value, find some equation that's missing one value and see is there a link. And generally there is. Okay, that's how you always do this. Part 2. Okay, so I'm going to rub this out. Okay, so once you've seen it, you can always go back in the video anyway. So part 2 says we get a different block of wood now. The block of wood is... Actually, get rid of that force because we don't need it. Oh no, we do need the force. The force stays the same. That doesn't matter. I'll work around it. F equals 160. Okay. All right. So part 2 then. I'm going to keep these values on the left, same values. All right. So calculate the velocity of the bullet emerging into the block is only 0.5. So we change our S value from 0.5 to 0.25, okay? The bullet stays the same at 200 meters per second. The mass is the same. Okay, all right. So what do we need to do here? Calculate the velocity. All right, so we're looking for v this time when it leaves the block. Okay, so we're looking for v as it leaves the block. So we don't need this v this time. So v equals v. So obviously, ek equals a half mv squared. Make v the subject of your formula here. So that becomes v equals, so multiply across by 2, ek divided over m, and square root to get rid of your 2. We have every value here except ek, so how do we find ek? Look back to the previous question, what did we do? We use work done. Can we use work done now? Yes. Okay, so work done equals ek. All right, so work done is force times distance. This time, of course, that's going to be 160 times 0.25, which of course just gives us a value of 40 joules. Okay, but 40 joules of what? No, actually, it works out this time that if you made a mistake here, the following bit, you would have actually gotten away with it. But just be aware, careful. Okay, so what this means is that the block of wood, okay, can do 40 joules. So it's a loss of ek. Okay, because it's half, the block of wood is going to reduce. Okay, so we know at 0.5 meters, okay, the block will stop the bullet. All right, so obviously at 0.25 meters, it's only going to slow it down by a half. All right, but I had to show you all the maths, okay, because sometimes it won't be so clear cut as a half. It could be a third, a quarter, just a random number. It could be 0.4, okay, and that's a lot of, so you need to do this maths this way, okay. So it loses. So this time, when it's 0.5, the block will completely stop the bullet, okay. So its loss in kinetic energy is the same as the kinetic energy of 80, so it takes 80 out of it. This time, it's only going to slow it down by 40 joules. Okay, so it's a loss of ek. So how much kinetic energy is left? Well, we know from the previous question, the total ek was 80 minus 40 equals 40. So the answer was 40. So if you forgot to do this step, the loss in ek, it would have been okay because the work done was 40. But just to be aware of that. Okay. All right, I'm gonna have to rub out the top bit here because I need my space. Okay. So all you do is you bring this up here. So v now equals the square root of 2 times 40 over 0.004. And that should give you a value of 141.4 meters per second. Okay. Okay. So there you go. That's generally kind of the way these kind of questions go. I think this came up in an exam paper actually once. All right, so we're close to halfway now. All right, so we're going to look at potential energy next. All right, so potential energy, again, loss of potential equals gain in kinetic, loss in kinetic, gain in potential. So what is potential energy? Is the energy of an object has due to its position in a force field. You have to use the whole definition. You can't say the energy an object has due to its position. What do you mean by position? Position in a force field. In other words, if your pen is on the ground, okay, its potential energy is obviously 0, okay, because chances are it's not going to go anywhere. If you put your pen on top of your desk, its potential energy is now increased, okay, because its displacement from the ground has gone up. All right, it's why if you have a book, if you drop a book from a very low height, it makes a small sound, but if you drop a book from a very higher height, it makes a loud sound. Why? Because it had more potential energy. So when it hit the ground, that potential energy had changed to kinetic energy, and bang, okay? That energy then got released as sound and heat, okay? Now here, this bit here, the two types, use strain and potential. Strain is basically elastic, okay? So elastic, elastic bands, the more you stretch them, they stretch out, and then when you let go, the faster they'll snap back together, okay? Obviously, you go too far and you snap them, okay? That's strain, all right? Now, we won't really be looking at that too much, okay? The real thing we look at is gravitational. Now, gravitational is basically the one we examine in mechanics. It's also very important because it's going to come into play now when we do circular motion, okay? So gravitational potential energy is an energy a body has because it can fall to a lower level due to its weight, okay? So the three factors involved here are mass, acceleration due to gravity, and distance apart, height, okay? Distance apart, height. Okay? So mass, gravity, height. They're the three factors, all right? And as I said, that's why the higher you hold the book, the greater the bang it's going to have when it hits the ground. All right, so a particle of mass, 20 kgs, is thrown upward through a vertical height of, and also we are going to assume here that gravity is 9.8 equals g. So your potential energy, mgh, fire in all your values, and you should get an answer of 117,600 joules, okay? Because you've mass of 20, height of 60 or 600, and gravity of 9.8. Problem 7. How far above the surface of the Earth must a 4 kg mass be raised so that its potential energy is increased by 4,000 joules? Okay. So we've mass 4 kgs. We have potential energy 4,000 joules. We have gravity 9.8. We're trying to find height. So EP equals mgh. They want h to be the subject of the formula. So h equals EP over mg. That's it. Okay. Rearrange it. They're asking for an equation or a value h. So we make that the subject of the formula. And then you continue on. Okay. And that should give us a value of 102 meters. There you go. Okay. Very straightforward. You see, these questions aren't overly difficult. Okay. Right. So, a body of mass, 100 kgs, is at rest at a point A, which is 50 meters above the ground. All right. Let's put all the values in. Mass on 100. Height 50. That should be 100. That should be 100, not 106. Height 50. What is the potential energy of the body at A? Gravity is 9.8, as always. And we're looking for EP. I'm just going to call it E here. Okay. Taking the ground as 0 potential energy. So in other words, that at 50, the ground is 0. That's fine. Be careful with that. Sometimes they can change that to make the ground a certain percentage of potential energy. But generally we assume, unless stated otherwise, it's 0. Okay? So we're 50 meters above the ground. What's the potential energy of the body at that point? Well, that's fairly straightforward. E equals mgh. Sub in your values, and you should get 49,000. Don't forget your SI unit, joules. And then, always, go back and read the question. Don't ever just assume you've answered the question and move on. Go back, read the question. Have you answered it? Okay, so we've answered this bit, but we haven't answered the next bit. What is the kinetic energy of the body when it has fallen a distance of 20 meters? So kinetic energy is half mv squared. Okay, so we have the mass. Let me see, we have gravity. So some people could go off and try and do the equations of motion to find out the velocity. I've seen people do that. However, if you remember the following, you don't need to. EP loss equals EK gain. Okay, so what we lose in EP, we gain in kinetic. Okay, so therefore we've dropped 20 meters. Okay, so we've fallen this is 20 meters. So H is 50 minus 20, which equals 30. So where currently our height is 30 meters above the ground. You see? So now we just simply say EP equals 100 times 30 times 9.8. So our new potential energy is 29,400. So at 30 meters above the ground, we have a potential energy of 29,400 joules. So it's 49 minus 29 equals, not 29. I thought it was 29,000. It's 29,400. So I'm going to have to write it all out. So 49000 minus 29400 gives me 19,600 joules. So that's what we've lost. So by dropping down to 30 meters, we lose 19,600 joules of potential energy, which means we gained EK 19,600 joules. You see? What you lose in potential, you gain in kinetic. What you lose in kinetic, you gain in potential. Okay? Kinetic energy is generally at its max just before it strikes the ground. Okay? Potential is at its max, the highest point from the ground. Kinetic is at its max, the lowest point from the ground, which is basically right before it strikes the ground. Okay? So there you go. That's the easy way to do it. Instead of some people now, I think I saw something before, they basically use the equations of motion to find V. And then when they found V, they subbed it back into half mv squared and got the answer. That's fine, but it's way more difficult than just basically remembering loss of potential is gain in kinetic. Okay? Always try and do the simple answers. The simple answers in physics are generally the correct ones. All right. I think this is the last question before we move on to the next thing of power. So we're almost there. So a mass of 120 kgs traveling at 30 meters per second collides with and sticks to a mass of 15 kgs, which is at rest. Find the velocity of the combined mass after the collision. Find also the loss of kinetic energy. Okay. I gotta roll this up because I want all the space here. So we have a mass. Actually, hold on a minute. Yes, there's a mistake there. That's not meant to be 120 kg. That's meant to be 10 kg. That's a typo. All right, so it's 10 kgs traveling at 30 meters per second, collides and sticks. In the book, it's page 132, question 8. So it was a typo on myself. Right. So mass traveling at 10 kgs. Oh, sorry, not traveling at 10 kgs. A mass of 10 kgs. Apologies. Traveling at, which is a U. That's meant to be a U. Traveling at 30 meters per second. Collides with and sticks to a mass of 15 kgs. M2. So I'm going to call that M1, U1, and it's at rest. So U2 equals 0. Find the velocity of the combined mass after collision. Find also the loss in kinetic energy. So we're looking for V equals V, and we're looking for EK equals EK. All right. So straight away, it's an equation of motion, the collisions. Second you see collisions, go to your log tables. There's only one equation there. M1 U1 plus M2 U2 equals M1 V1 plus M2 V2. That's the one in the log tables. Okay? Now, we're told that they stick together. Okay? So, collides with and sticks to. So if they stick together, what does that mean? Well, what it means, if they stick together, that means their velocities are the same. Because they stuck together. They have the exact same velocity if they're stuck together. So V1 equals V2. So you rewrite this equation, M1 U1 plus M2 U2 equals M1 plus M2 times V. The reason it's that is because these two have now stuck together. They're now one combined mass and they have one combined velocity. So what do? We're looking for V. you sub all your values in, okay? So basically, I'm just gonna, because it's obviously with the pen not really working so great, I'm gonna rearrange this equation. First, m1 u1 plus m2 u2 divided by m1 plus m2 equals v. So you don't have to do it this way. I always do it this way. I find it neater to keep everything in its symbols and just rearrange it, okay? But if you prefer, you can obviously, of course, put your values in up here. You can put your values in up here and work it out that way, okay? But anyway, sub all your values in, let the calculator do the work, and you should end up with 12 meters per second, okay? 12 meters per second. Now, to find also the loss of kinetic energy, do I have enough space down here to just do that? No, okay. So I'm gonna have to rub this out, okay? So let me just put in my new value there. 12 meters per second. Okay, so that's how we do that. Fairly straightforward. It's the collisions, rearrange it, get your V value, make V the subject of the formula, put in all your values, and you should get 12. If you can't get 12, please leave a comment on the Edmodo page or in the comment section there, and I'll try and get back to you. All right, so now part 2. Part 2 says, find the loss in kinetic energy. So EK equals a half mv squared. I'm going to put that down here just so I need all my math space. A half mv squared. All right, so what we're going to do, so loss in kinetic means, I know, gain in potential, but here that's not really what it means. Loss in EK equals initial minus, that should be an M, not an M. I don't know why it came out like an N. Okay, so initial minus final. Okay, so that's the loss. What did we lose? Okay, initial minus final. Okay, because we obviously slowed down. So we got to find the initial first. All right, so that's what we're going to find first. Initial. So EK equals a half 10 times 30 plus a half 15 times 0. Where did I get those values? Well, this is car 1, okay, object 1, sorry, which was traveling at 10 meters per second or had a mass of 10 kgs and traveling at 30 meters per second. And the second one down here, that is M2 because it was a mass of 15, which is at rest. You see, add the two together. Obviously, of course, this is going to be 0. Okay, so it's basically just a half 10 by 30. So EK initially works out to be, oh, I forgot a value. Hold on a minute. I forgot to square that. There you go. I nearly always forget to put in the square. So it's actually 10, because 10 times 30 is 300, and then divide that by 2. Okay, so it's actually 30 squared. So that gives us a much larger number. That makes more sense. 4,500 joules. That's the initial. Final, EK, is equal to a half 10 plus 15 times 12 squared. Where am I getting that value? Well, it says, okay, it says that collides and sticks with. So we're basically going to after the collision where the two masses have stuck together and they move off with the one value. So that's 10 plus 15, and the one value is of course their velocity after, which we worked out to be 12. So my value here is 1800 joules. So we simply subtract 45,000 minus, not 45,000, sorry, 4,500 minus 1,800. So our loss in kinetic was 27,000 joules. There you go, 27,000 joules. Okay? Are we okay with that? All right. So, collisions now. All right, so collisions, power, percentage efficiency. Okay, we're almost there. Hopefully you're finding this fairly straightforward to do. Okay, so collisions. Kinetic energy and momentum. When two objects collide, momentum is conserved. Okay, so again, that's the definition from previously. Momentum is conserved as long as no external forces act in the system, which is why in real life, when cars crash into each other, okay, momentum isn't conserved because obviously when they crash, the sound you hear, the bang, the bang is actually energy being converted into sound. So that's going to lose you energy. There's also a release of heat. That loses you energy. And also you've got the road, which is of course your tires are gripped to grip the road. The road is going to slow it down. You've got the wind, the air, all these things affect the momentum after collision, which is why in real life not in real life, but in if you saw a collision happening in real terms, you wouldn't observe the momentum happening. But we have, through calculations, proven that momentum is conserved if no external forces act in the system. So if you are asked to give that definition, do not forget that. They will knock 3 marks off if you forget it. Kinetic energy, as I said, kinetic energy is not conserved. This is because some of the kinetic energy gets converted to, and that's the big one, okay? Why isn't the energy conserved? It was an exam question, as I said here, okay? I don't know what you say is, this is because kinetic energy gets converted to sound and heat, okay? And the amount is on the elastic properties. In other words, cars are not very elastic, okay? So when they hit each other, there's going to be a lot of sound and heat given out when they crash, okay? Okay, renewable, non-renewable, I don't really think I need to go through that, okay? You should know that from junior cert, basically. Okay, power. 2 definitions for power. Either one works. I always go with the top one, okay? So what is power? Power is the rate at which work is done, okay? Power is equal to work done divided by time taken. You can, of course, give this as your definition. The lower one, you can give this as well. It's the rate at which energy is converted from one form to the other, but this is not in the log tables. Okay, P equals ET. Okay, what is in the log tables is power is equal to work done by time. Okay, the reason I did show you this one though is because it can help in some situations. The idea of converting energy from one form to another. So, for example, a question you get when we do electricity is, what's the power of a bulb if so many watts of light are given out? Okay, or so what's the power of the bulb if so much energy is converted from this much to light and heat of this much? And a lot of people get confused. Okay, but converting it from electricity to heat is an energy conversion. That's power, okay? Power of course, the watt, all right? Always remember the Harry Potter meme on my wall, okay? As cringe and all as it is, it'll remind you what the SI unit is. All right, so a car engine produces 600,000 joules of energy in 12 seconds. So we'll stick to the log tables to make it easier for you for the time being. Okay, so work done is 600,000 joules and the time is 12 seconds. So power equals work done divided by time. Put in those 2 values and we should get 50,000 watts. Okay? Very straightforward. Actually, all these questions are fairly handy. Power, really, we won't really see that now. You could get into mechanics question, but you really see it in electricity when we get to electricity. It comes up quite a bit then. So, a boy of mass 40 kg sprints up. So, mass 40 kgs sprints up 50 stairs, each of height 16. So, time 40 seconds. Find the average power. Okay. So first thing we need to find out, really, is we need to find power, which equals power. Power is work divided by time. So we need to find work. What is work? Work is force times distance. Okay? So we know we're looking for power. Power is work divided by time. So we need to find work. What is work? Force times displacement. We don't have the force. We also don't have the displacement, but we can find them. What is force? Force is equal to mass time acceleration due to gravity, which is 40 times 9.8. Okay? And I didn't work that out. I just left it as 40 times 9.8. So 40, 9.8. Displacement is, we have 50 stairs, and each one is 16 centimeters. 0.16. You have to convert to meters. So there you go. So you multiply this by this. So my work done should equal 3136 joules, and I'm out of space. Okay? So my force is mass times gravity, which is 40 times 9.8. My displacement is the height from the ground up, which of course is 50 steps. It should be steps, not stairs. 50 stairs, each of height 16 centimeters. That's a terrible typo. So it's a terrible English, more should I say. Should still be 50 steps, each of height 16 centimeters. So it's 50 times 0.16. Don't forget to convert centimeters to meters. So my work done is 313.36. Okay, so I'm going to have to rub this out to give me space to answer the second part. So power is work divided by time. So power is 3136 over 40. So my power here should work out to be 78.4 watts. Now, actually, if you forget what the SI unit for power is as the watt, look at it this way. Work done is joules and time is second. So you can also say joules per second. So if you're ever stuck and you can't remember a watt, think of it that way. Joules over time, okay? Joules over seconds. All right, so the last thing we look at here, the unit of electrical energy the ESB used for domestic power supplies is called a kilowatt hour. 1 kilowatt hour is the amount of energy given out by a 1000 watt appliance in 1 hour. Calculate the number of joules in a kilowatt hour. Oh, there's a lot of information kind of handed there. So we're looking for a kilowatt hour. So what is a kilowatt? 1,000 watts. Kilo means watts. Oh, kilo means 1,000. All right. So basically, what we're saying there is, all right. So power equals 1,000 watts. That's 1 kilowatt. It's the amount of energy given out 1,000 watts per hour, time, 1 hour, which is 60 by 60. 3600 seconds. You see? Calculate the number of joules in that. Well, power equals work done by time. The only one here that is in joules is that. So we're obviously going to make that the subject of the formula. So watts equals power by time. So we multiply 1,000 by 3,600. So our joules here, 3600, and then the 3 zeros for the 1,000. 1, 2, 3. 3,600,000 joules. Okay. Percentage efficiency. Oh, excuse me. All right, so with this, we're kind of moving on to the last bit now. These are kind of small things. The first thing to remember is, of course, there is no such thing as a 100% efficient machine. Okay? You will always lose energy in the process. Okay? For example, moving parts require energy. They're, of course, going to give out noise and heat. Okay? Always going to happen. So there's no such thing as an energy that's 100% efficient, like a laptop that's 100% of the electricity is going to go into running the laptop. It won't. Okay, you're going to lose some of the power to other things. Okay, like heat loss, things heating up, or movement or noise. Okay, that's why perpetual motion doesn't exist. Okay, it never will. Okay, because it can't. You'll always lose energy to some other formula. Okay, so the equation then to get this percentage efficiency is your output divided by your input multiplied by 100. That's basically it. Okay, how efficient are you? Okay. What did you put in? Or what did you put in? What did you put out? Okay? So the output divided by the input multiplied by 100. That's it. Or think of it like in maths. When you're working out your grade, if there's 100 questions and you got 60 right, you want to work out what percentage is that. Okay? Well, 60 divided by 100 multiplied by 100. Okay? 60%. All right. Solar constant. The solar constant represents the average amount of energy falling normally each square meter of the Earth's planet. I think I have a question there at the end. I don't But I'll come back to this solar constant actually in another topic. There is a maths question for it, but I'll go through it then. Okay. So basically, what the solar constant is that the sun will give an amount of energy per square meter of the planet Earth. Okay, and that obviously changes depending on the weather. Okay, but usually there is a maximum amount, obviously, that the sun can give. All right, we can from that. That's how they work out if they put a solar panel on your roof, how much electricity would it generate? Okay, by how long it gets exposed to the sun. Okay, all right. Problem 13 then. An engine has an input. So our input 5,000 watts. So in other words, the maximum amount of energy power this thing has is 5,000. Okay, I don't know what happened there. That jumped up. The output is 4,000 watts. Percentage efficiency, therefore, percentage efficiency is going to be our 4,000 divided by our 5,000 multiplied by 100. And that gives us 80% efficient. So it loses 20% to other things. That's all it is. Okay? Think of it always like an exam. Your grade divided by the total marks you could have got multiplied by 100. All right, so a petrol car engine is 25% efficient. So this time, it's slightly different. 25% efficient. That's incredibly low and terrible. Kinetic energy produced, so EK, is 130 kilowatts. 130,000 watts. The rest of the energy appears as heat. Calculate the rate at which heat is produced. Okay, so therefore, 75% is heat. Okay, so 75% is heat, 25% is the running of the car. Okay? Let me see now. So 25%. Okay. So there's two ways to do this. Okay. 75 is obviously 3 times higher than 130. So you could just multiply 130 by 3. And there you go. Okay. You see that? So that's a quarter. Oops. That's a quarter. That's 3 quarters. So you could, of course, just multiply your answer by 3, and you get 390,000 watts. And that's fine. Okay, that works for this. Okay, however, let's imagine that they were not so easy numbers to multiply that way. Okay, what would you do? Well, what you would say is you'd say, well, 130,000, we'll divide that by 25. Okay? Actually, do you know what, I'll do I have space down here? I do. So what we'll say, 25%, this is only if it doesn't work out to that nice, is, what did we say, 130,000. So what's 1%? 1% is 130,000 divided by 25. Well, we're looking for 75%. So that's 130,000 divided by 25 multiplied by 75. Okay? So if it doesn't work out, so like let's say it was 28% efficient. Okay? So therefore it was 72% inefficient. It's not nice round numbers. Okay? So this is how you do it. 25 equals 130,000. So 1 equals 130,000 divided by 25. 75 is 130,000 divided by 25 multiplied by 100. That should give you an answer. No, percentage efficiency, 390,000 watts. And that's it. There you go. That's how you work out the percentage efficiencies. It's been a long time since I've seen an actual question like that come up though. Okay, I must be honest. So I wouldn't lose too much sleep over it really. All right. And even then, it's also fairly straightforward. Just keep it simple. The simple answers, guys. You do this in maths as well, I'm assuming. To estimate the power. Yeah, you could revise this. This is basically just going back over those questions again. Okay. That is work, energy, power. That's topic 10 complete. If you have any questions, leave them on the Edmodo page.